Every so often here on Weather World, we like to introduce you to some of the new faculty members here in the Department of Meteorology and Atmospheric Science, and this evening is one of those times. Dr. Anthony Didlake joined the faculty in January 2016. He specializes in tropical meteorology and radar meteorology and the intersection between the two. Welcome to Weather World, Anthony.
Thank you. It's nice to be here.
So what got you interested in tropical meteorology, and have you been able to realize any dreams of flying into any storms?
Well, I was always interested ever since I saw Hurricane Andrew from far away. When I was in Detroit and I saw the weatherman with the storm just being in its circular nature, that always attracted me. And I was able to fly into a storm in 2010 in Hurricane Carl when I was doing my graduate research, and that was an amazing time.
Now, our viewers are used to seeing radar images. We show them all the time, but those are from land-based radars. You use airborne radars to study the structure of storms. What are some of the key differences between the land-based and the airborne radars?
So these radars, all of them, one thing that they have in common is that they can measure the velocity. But land-based radars are just one radar that allows you to look at just one direction of the wind. With airborne radars, we're able to go out into where the storm is in its natural habitat over the ocean, and they're actually two radars on one, and they can map not just one dimension of the wind, but all dimensions of the wind. So that's one of the major differences, is getting the three-dimensional winds.
And you also use data gathered from Spaceborne radars, radars on board satellites. How do those add to the work that you do?
Well, one of the limitations with the land and the airborne radars is that they can only get you the data where you can get your land-based radar and your airplane. With spaceborne radars, we're able to look at all of the storms around the entire globe. We can't get the winds from the spaceborne radars yet, but we can get the precipitation mapped in three dimensions across the entire world at all times.
Which, of course, can be very useful because we can get a sense for how much rain these things are dumping when they're out over the oceans to improve forecasts once they get to land. So what are some of the most exciting problems that you're working on right now?
The most exciting problem I'm working on now is eye-wall replacement cycles. So eye-wall replacement cycles occur when you have a very mature eye wall, but around that eye wall you can get more convection and more storms that form a ring. And when that ring forms, which is a secondary eye wall, that can contract and eventually collapse the inner eye wall. And that causes very distinct structural and intensity changes in the storm. And so my work now is trying to better understand this eye wall replacement process, both in terms of understanding how the rain bands form the secondary eye wall and how the secondary eye wall changes the size and intensity of the storm.
And I mean, briefly, how common are these? Does it happen in every storm?
So they happen in a lot of storms, specifically the stronger storms, depending on where you are in the world. In the Atlantic Basin, most of the Category 3 hurricanes undergo eye wall replacement cycles if they aren't interacting with other deterring effects, such as the land a big jet stream.
So what are one or two observations from this past hurricane season, which none of us will soon forget, that kind of stuck out to you as demonstrating that we still have a long way to go in understanding not just eye wall replacement cycles, but how tropical cyclones work?
So what stuck out to me was the fact that we had such variety in the intense storms. So with Harvey and Irma and Maria, they were all really strong storms, but they were all of different sizes. They all behaved differently. And even though they each also underwent an eye wall replacement cycle, they had very different characteristics in terms of their strength and how it recovered from that eye wall replacement cycle. So just the variety of the different storms lets us know that we still have a long way to go in predicting which one will actually change in intensity and size.
What's one piece or type of data about tropical cyclones that if we had it or if we measured it better, you think we could make the biggest leap forward in understanding them? So there are several pieces we need. I'll go through just a couple. Like we need to have better measurements and more measurements of the boundary layer. So this is where the hurricane gets all of its energy, is from the sea surface. And so a lot of the moisture and temperature and pressure information near the surface and the boundary layer is something we need really
better measurements to understand how the energy of the storm changes. And we also need more moisture information, so the humidity above the boundary layer as well. Something that's not easily measured, but that's something that we need.
Right, and to get those boundary layer measurements, you're talking about the lower part of the storm where you can't really fly in there, so you need to find more remote ways to get the information. Dr. Anthony Didlake, one of our newest faculty members here in the Department of Meteorology and Atmospheric Science. Thanks, Anthony, for stopping by.
Thank you for having me.
And we will be back in a moment with a recap of the short-range forecast.